Hello, this video we are going to be discussing magnetic flux and electromagnetic induction with Faraday's law and Lenz's law. So first, let's define magnetic flux. So magnetic flux, represented with the Greek letter phi, switch to Y, represented with the Greek letter phi, is going to be equal to the dot product of B, the magnetic field vector, and A, an area vector. So what this means is, let's just say we have a loop of wire here. Now the area vector is going to be perpendicular to this loop in a chosen direction. So we arbitrarily choose one direction to be of this area enclosed by the loop to be the direction the area vector points in, but the area vector must be perpendicular to this to the area of this loop, um, and it also has the magnitude of the area of the loop. So this is the area vector. Now we arbitrarily choose it to point this way, but it could also point in the opposite direction, again, as long as it's perpendicular. And the reason that this doesn't matter is because based on the direction we choose, um, the flux will either be positive or negative, and the EMF induced will also have to be either positive or negative. But if we choose the opposite direction, the sign of the EMF will be the opposite sign, which means that the direction of current flow will be in the opposite direction in the opposite if we will be in the opposite direction around the loop if we choose the opposite area vector. But that works out because if you flip the loop 180 degrees, it will seem like the current is flowing in the opposite direction. And so the direction you choose right now doesn't matter, again, as long as it's perpendicular to this area here. Now, this B vector here is just a magnetic field vector. And so the flux is just the magnetic field vector dotted with the perpendicular area vector. And one way you can think of this is it's almost like the amount of the magnetic field that's crossing through this area vector, or this area surface here. Or not really surface, but like this enclosed area by the loop. So let's just say you had a loop that was flat here. And so it's in the plane of this page. And then you had a magnetic field that was going across, so it's parallel to this loop. Then we know that the area vector here is either going to be going directly into or out of this page, which means that the dot product between them is equal to 0. So in this case, flux here is equal to 0. And we see this is true because none of these magnetic field lines are crossing through this loop. None of them are going through the loop. They're only passing parallel to it. However, if we have like a loop like this, and the magnetic field is going into or out of the page, so if this was the magnetic field, we see that there are magnetic field lines going through the loop here. And what that means is that the flux is going to be non-zero. So if we choose our area vector to be pointing out of the page, then this time the flux will be positive, will be negative. Or if we choose the flux to be, if we choose the area vector to be pointing into the page, then the flux will be positive because it's in the same direction as the magnetic field. But again, um, if the magnetic field and this area enclosed are not parallel, then the flux is non-zero. So this has non-zero flux. And again, you can think of this as the flux is going to be almost like the number of field lines that cross through this enclosed area by the loop. Now, we can examine how a flux causes, or how change in flux really causes EMF to be induced in a loop. So that comes from Faraday's law. So Faraday's law states that change in flux here, or EMF, so Faraday's law states that EMF is going to be equal to uh, negative, or here it's negative N, so d phi over dt. And now what this what this means is you have EMF here. So this is EMF, and here is going to be the number of turns. And so this is for like coils. So N applies to coils. So if you have multiple loops of wire right next to each other or on top of each other, then N is the number of turns. And we'll explain why this is here later. And then this is going to be the derivative of the time derivative of flux, or change in flux over change in time. So this is change in flux. And so we see that from this law, Faraday's law, change in flux produces an EMF here. Okay, so let's examine how this works. Let's just say we have a loop here. Let's say we have a loop, and then we have a magnetic field that is going into the page like above. So there's this magnetic field going into this page. Now, if we change the magnetic field, so remember flux is equal to B dot A. So if we change either the area of this loop, or we change the strength of the magnetic field, or the direction of the magnetic field, then we can change the flux through this loop, which will then induce an EMF. And so let's just say the magnetic field is decreasing over time. So let's just say that we have so the change in the magnetic field over the time is less than 0, so it's decreasing. Now we know that there has to be an EMF induced, because we know that EMF here is equal to negative n. We can just exclude the n right now because we're only working with one turn, so n is 1 times, or d flux over dt. In this case, since the area is constant, this is just going to be equal to negative A over times dB over dt. Now, let's examine what this negative here means. So you notice that there's a negative sign in this equation. And this is very important because the negative sign, that is Lenz's law. And Lenz's law states that the induced EMF will always act in the opposite direction of the charge or the EMF that causes it. And so basically it reduces it. The Lenz's law states that the induced EMF will work to resist changes in the system. And so let's examine how this applies to this situation. We know that the magnetic field is decreasing, and so there's an induced EMF. Now this EMF is going to work against the decrease in the magnetic field, meaning that so in order to keep the system similar to the way it originally was, if the magnetic field is decreasing, this EMF has to induce a magnetic field that is in the direction of the original magnetic field. Because if the magnetic field is decreasing, then the EMF has to create a magnetic field to counteract the decrease of the original magnetic field. And so since the magnetic field is going into the page here, and it's decreasing, this EMF will have to create a magnetic field going into the page to counteract the decrease. And so if the magnetic field is going into the page, we know by the right-hand rule that this EMF is going to create a clockwise current in this scenario. Now, what happens if this change in magnetic field strength is greater than 0 over time, meaning that the magnetic field is increasing over time in strength? Well, then we see that since the magnetic field is increasing over time, we still have this equation here that works, and so we know that an EMF must be induced. But if the magnetic field strength is increasing over time, we know that by Lenz's law, the induced EMF will have to counteract that increase, which means it has to produce a magnetic field in the opposite direction to counteract the increase of the magnetic field, of the original magnetic field, which means that the magnetic field is going to be pointing out of the page, and so this leads to a counterclockwise current by the right-hand rule. Okay. And then again, because flux is equal to B dot A, we know that not only do changes in the strength of the magnetic field matter, but also in the area of the loop. So let's just say the loop was getting smaller. So if the loop was getting smaller, then area would be decreasing, and so flux would be decreasing. And we see that with a decrease in flux, we want to counteract that with an increase um, by Lenz's law. And so if flux is decreasing, then we want to create a magnetic field into the page to increase the flux into the page. Because if we assume that flux is positive, that means that again, a decrease in area will lead to a decrease in flux if flux is positive. And for flux to be positive, that means that our area vector is lined up with this magnetic field vector. So if you decrease the flux, there's going to be a current clockwise in this view to counteract that decrease in flux. So again, so decreasing the area has the same effect as decreasing this magnetic field. And again, this all depends on the direction you choose for your area vector. So let's just say you choose the if you choose the area vector to be pointing out of the page in this scenario, then it's going to be negative because this magnetic field vector and the area vector are in opposite directions. That means that when you decrease the area, the magnetic field, the flux is going to get less negative, or flux is going to be increasing. So you want to decrease the flux. And by decreasing the flux, if the area vector is pointing out of the page, then the induced magnetic field will have to be pointing into the page, which gives the same result as if we chose the area vector on the opposite direction, which we have explained before. So again, the direction of the area vector doesn't matter as long as it's perpendicular to the area that we're trying to observe. And one more thing, by the dot product, we know that the dot product here, so flux is equal to B dot A. But what this means is also that magnitude of flux is going to be equal to magnitude of B times magnitude of A times cosine theta. So if we change the direction of the magnetic field or the area vector, basically if we change the angle between them, then the flux will change. So let's just say we have a loop rotating in a magnetic field. Even if the magnetic field strength doesn't change and the loop's area doesn't change, this angle between them will change, which will induce a current inside the loop because of the EMF from Faraday's law. Okay, so let's examine a classic case of Lenz's law. So let's say that we have a loop of wire here, and then we have a magnet. And so this magnet, let's say that this is the north end and this is the south end. So what will happen if we bring the magnet closer to the loop? How will the loop react? Well, we know that there is going to be a change in flux. So let's just say the area vector of the loop is pointing to the left. And so let's just say this loop here right now is going to be perpendicular to this magnet, and the area vector is going to be pointing to the left here. So it's going to look like this. That's the way we choose our area vector. Then you know that the magnetic field of this magnet is going to be going from north to south. So it's going to look like this. I'm only going to draw it from the north end. But the magnetic field looks like that, basically, at the north end. So now we know that flux is positive. But as we bring this magnet closer, we see that the number of field lines crossing through this area increases, or basically, the magnetic field strength increases as we bring the magnet closer to this loop. And so if the magnetic field strength increases, then we know that the flux is going to increase as well. So right now, if we have magnetic field increases, then flux increases. And if flux increases, then by Faraday's law, we know that EMF, the induced EMF, is negative. So it decreases basically from zero. Now, since this EMF is negative, really I should write, so this flux is increasing, which means EMF is negative. And the negative EMF means by Lenz's law, it's going to counteract this change. And so if the magnet is getting closer, there will be an induced magnetic field here in the opposite direction. So this is going to be the induced magnetic field, which means that the current has to be running by the right-hand rule. The current has to be running this direction. So let's just say that this side of the loop is closer to you. So this side of the loop right here is closer to you than this side. And so the current is running in this direction here to induce a magnetic field in this direction. Okay. And so we can easily determine the direction of the induced magnetic field because it always opposes the EMF change. And so since this magnet is getting brought closer to maintain the system as it previously was, so to resist a change in the system, we see that by Lenz's law, this induced magnetic field will oppose this magnet's permanent magnetic field. And so why this makes sense is because if you have, let's just say this loop and this magnet were at length L apart, by bringing the magnet closer, this L is decreasing. But since by Lenz's law, this system tries to resist changes, this magnetic field will work in a way to keep L constant. And so if this magnet is getting closer, then the magnetic field induced will be in the opposite direction as this magnet's magnetic field, so that the loop repels the magnet and tries to keep this L constant. Now let's just say that this loop here was, let's just say that this magnet was actually getting brought or pulled away. What happens if the magnet is getting pulled away from the loop? Well, then you could go through this process and say that the magnetic field strength is decreasing, so flux is decreasing, so EMF has to be positive. But you can also just look at this right away and know if the magnet is getting pulled away, then this L is going to try to increase. And so the loop, by Lenz's law, will have an EMF induced that tries to resist this increase in L, which means that it's going to try to decrease the distance between the loop and the magnet. And so that means that this induced magnetic field is going to attract the magnet because it's trying to counteract this increase in distance between them. And so that means that this magnetic field will be in the same direction as this magnet's magnetic field, which means that it's going to be to the left here, and that means that the current is going to flow clockwise, or the current is going to flow, it's hard to say clockwise or counterclockwise since we're looking at it perpendicular. Since this loop is perpendicular to the page, kind of, but it's going to flow in the opposite direction. So again, it's always going to counteract changes in the system. So if the magnet is getting brought closer to the loop, then the loop will try to push itself away from the magnet. And if the magnet is getting pulled away from the loop, then the loop will try to pull itself towards the magnet. And that's how you can easily find the direction of the magnetic field and EMF induced by like a magnet moving towards a loop. Now, if we were to flip the magnet, say like the south side was on the left and the north side was on the right, then the direction of the induced EMF will be the opposite, and the direction of the induced magnetic field will also be opposite. But the effect is going to be the same because, again, if you flip the magnet, then EMF is going to be in the opposite direction, and then this magnetic field is going to be in the opposite direction, but the magnetic field of the magnet is also going to be in the opposite direction. So all those cancel out, and so even if you flip the magnet, bringing it closer causes the loop to produce a magnetic field that tries to push the magnet away, and bring the loop away from the loop. Bring the magnet away from the loop will create or induce a field in this loop that tries to bring the magnet back closer to it, again, to maintain this state of the system before the magnet started changing position. Okay, now let's examine another application of Faraday's law, and that is with coils. Okay, so, and let's say we have a transformer, and what a transformer does is, like its name says, it transforms voltages, and you can see, like, you can think of it as transforming voltage, but in turn it also changes current as well, or possible output current. And so let's just say you have um, a really simplistic model where you have an iron bar or some uh, magnetic, or you have some ferromagnetic material in the middle here. And then you have a loop on one side of this bar. And then you have another loop on the other side of this bar. Now, if this loop 1 has n1 number of turns and the second loop has n2 number of turns, then if you produce a change in voltage through here, what is going to be the output voltage on N2? So that is the question we're trying to answer. Now, if you produce, or if you have a direct current going through this loop, then the voltage EMF, or if you have a constant current going through this loop, then there's no change in flux because the magnetic field produced by this loop is going to be constant, which means that if the magnetic field produced by this loop is going to be constant, so let's just call this red loop the input, then there's going to be no change in flux in this output loop, which means that there's going to be no induced EMF. But let's just say we have an AC voltage, so an alternating current through this input loop. Then, since the current is constantly changing, the induced magnetic field by the right-hand rule is also going to be constantly changing, which means that there's going to be a change in flux in this output loop, and that in turn produces an EMF across its output. So we know that EMF here, or we know that EMF is going to be equal to negative n, and then change in flux. So a change in flux over time. Now notice that since they're both wrapped around the same core, a change in flux or a change in magnetic field, so the area stays constant between them because this is like a singular rod. But a magnetic field induced by this coil will be the same magnetic field that this coil experiences. So we know that for both of these, the areas, area 1 is equal to area 2. And then we also know that flux, which means that the change in flux, or sorry, that's there, change in flux 1 is going to be equal to change in flux 2. And then again, both of these are over time, the same time period. So knowing this, we know that basically E1, so we know that since the change in flux is constant, we know that E1 over N1 is going to be equal to E2 or EMF2 over N2. which means that if we want to find the output EMF is going to be equal to the input EMF times N2 over N1. So we know that from this we see that the output voltage basically between these 2 points, or between these 2 wires, is going to be directly proportional to the ratio of or it's going to be the ratio between the input and output voltage is going to be equal to the ratio between the input number of turns and output number of turns. So if you have a higher ratio of output turns to input turns, then this output EMF is going to be higher. And if you have a lower number, so let's just say this input is 5 turns and this output is 1 turn, then this output is going to be 1/5 the voltage of the input. But if the output has like 20 turns and this input has 5 turns, then the output voltage is going to be 4 times the voltage of the input. And now we have to see, so based on this, you can see that if you just make the output turns really, really high, let's just say 1,000 turns on the output versus 1 turn on the input, theoretically you could produce a voltage on the output that is 1,000 times the voltage on the input. Now this seems to be violating the conservation of energy, but we know that we cannot violate the conservation of energy, so we know that the power in is going to be equal to the power out. So we know power is equal to voltage times current. So V1 times I1 is equal to V2 times I2. So, which means that if we know that, so we see that V1 over V2 is equal to I2 over I1. And now if we rearrange this equation, so we have E2 over epsilon 1 is equal to N2 over N1, and we substitute this, then we get that I1 over I2 is equal to N2 over N1, which means that this output current is inversely proportional to the number of turns. And so what that means is that if you have a really large number of turns on the output compared to the input, then this output current is going to be much less than this input current. And if you have a really small number of turns of the output compared to the input, then this output current can be larger than this input current. So this leads to the conservation of energy, and this is why it is possible to increase or decrease this voltage without violating conservation of energy, because current also increases like accordingly or decreases accordingly. And the reason, again, that this N here is in front of this Faraday's law of induction is because when you have multiple loops together here, the total flux, the total flux going between all these areas is just going to be the number of loops multiplied by the flux, change in flux through one of these areas, because when you have these loops, they're so close together that change in flux through one of them is going to be the same as the change in flux as the one right next to it. So that's the way that that's why there's an N in front of this, that's why the N is there in Faraday's law. Okay, so let's go through one more example, and this is going to be motional EMF, or what happens when you like move a conductor through a magnetic field. So let's just say you have like this U-shaped frame. So like this is a conducting material, and then you have a magnetic field that's going into the page here. So there's like this magnetic field going into the page. And now let's just say you have some wire here, and this wire is moving with a constant velocity towards the right. And we want to find what is the direction of the current through this loop here if the wire is moving at a constant velocity to the right. Well, we know here that the magnetic field doesn't change, but the area does change. And so if we see that the length of the wire here is L, then we know that area is going to be equal to L, or the change in area over time is going to be equal to L times this change in, if we call this X, if we call this distance X here, then the change in area over time is going to be the length times change in X over time, which we see that this term is just equal to LV. And so this change in area over time is going to be equal to LV. Then we know that since the magnetic field is constant, then we know that, so flux, change in flux over time is going to be equal to magnetic field times change in area over time, which is then equal to BLV. And so that means that the magnitude of the EMF induced, so magnitude of the induced EMF is equal to BLV. And now let's find the direction of this. So we know that since this the flux, or since this area is increasing, if we choose our area vector to be pointing into the page, so aligning with the magnetic field, we know that the flux is also increasing, which means that we want to counteract that increase in flux with a induced magnetic field in the opposite direction. So we know that the induced field is going to be out of the page. And so if the induced field is out of the page, that means by the right-hand rule, we have a current going counterclockwise through this loop right here. So this current here is going counterclockwise. And so by this, we create a, so if there's a constant velocity, so if this bar is moving at a constant velocity, the induced current is going to be counterclockwise in this scenario. Another way we can look at it is if we look at this bar is going to have electrons in it. So I'll represent these electrons like here, like these dots here. Now, if the magnetic field is going into the page, and this bar is moving with a velocity to the left, that means that each of these electrons are also moving with a velocity to the left. And then now we can use the Lenz force, or we can calculate the force on, or we can see the direction of the force on these electrons using the equation for Lenz force. So we know that force is equal to force is equal to Q V cross B. And now, since the velocity of these electrons, the Q here is negative because this is electron, or these are electrons. And so we see that the Q is negative, and then V is going to be in this direction. B is going to be into the page. So by using the right-hand rule for cross products, or like the left-hand rule for finding the force, the magnetic component of the Lenz force, we see that since the magnetic field is going into the page and the velocity is going to the left, or the velocity is going to the right, but since it's negative, we can consider the velocity of a positive charge going to the left. We see that the force on these electrons is going to be downwards, right? So the force of these electrons are downwards. That means the electrons are going to travel downwards. But since electrons are negative, we see that if the electrons are traveling downwards, then the current induced is going to be upwards. And then this makes sense because it matches here. So we see that this current is going to be upwards, but since the electrons are forced downwards by the Lenz force, which means that there's going to be induced current upwards. So this is these are two ways of finding the direction of a current from like a moving conductor in a magnetic field. And so we see that like here, you can use Faraday's law and Lenz's law to find the direction of the current in this scenario, with the direction of the current in the scenario with the right-hand rule. And then here we can see that you can use the Lorentz force and the electrons, or the actual charges inside the conductor, to find the direction of the current induced when this moves, when this conductor moves through the magnetic field. And one more way of looking at it is, let's just say that we have again this bar here, and then it's moving with a constant, so it's in a magnetic field going downwards, or into the page, not downwards, and it's moving with a constant velocity in this direction. If this bar is moving with a constant velocity to the right, that means that there has to, think about it like in order to move it to the right, there has to be a force, an applied force to the right to move this bar to the right. But since it's moving at a constant velocity, there has to be another force that counteracts this applied force. And so this is the magnetic force or the magnetic component of the Lorentz force. Because again, to move this bar to the right, you have to apply a force to the right. But since it's moving at a constant velocity, the Lorentz force, so the induced, the force from this current through the bar from the magnetic field, is going to be counteracting the applied force in the opposite direction and in the same magnitude. And so if we know that the force is going in, if the force the bar produces is to the left, to counteract the applied force that you give it and makes it go at a constant velocity, if the force is to the left and the magnetic field is going into the page, then, so again, if the force is to the left and the magnetic field is going into the page, then the current has to be going upwards. So if you apply a force to the right on this bar, then there will be an upwards current to produce a counteracting magnetic force to the left, allowing this bar to go at a constant velocity. And this is again by the Lorentz force. So again, the reason that this is at a constant velocity, I'll say it again, is because in order to make it go to the right, you have to apply a force to the right. But since it's at a constant velocity, the induced magnetic field, or the force, the Lorentz force from this bar, has to be to the opposite direction of the applied force in order for this velocity to be constant and not accelerating. And so if the force from the magnetic field is counteracting the applied force, that means the current through the bar has to be upwards, which is consistent with these other two explanations of the direction of the current. Okay, so that is motional EMF. Remember, the magnitude of the induced EMF is going to be BLV, and then there are various ways here you can see of finding the direction in which the current moves. Okay, and then one more thing you can see is, let's just say you have a bar here, and then you produce a current through the bar. So this is almost like a railgun, or how a railgun works. So again, let's just say you have these two rails, or like let's just say you have a conductor here, and you have these two rails on this conductor, and you have like a magnetic field. So yeah, let's just say you have a magnetic field going into the page here. And so if you provide like an EMF, so if there's a voltage difference between these two bars, then there's going to be a current flowing downwards here. So let's just say that this is positive, this side is positive and this side is negative, and between these two areas there exists a voltage or a potential difference. Then if there's a current flowing through this bar here, then by this Lorentz force, we know that since the magnetic field is going into the page and this current is flowing downwards, there's going to be a force on this bar that causes it to accelerate towards the right. So, like, if you think about how a railgun works, like you have this conductor that's lying on two rails where there's a voltage difference between them. Then a current flows, and with this magnetic field, the flowing current and the magnetic field produce a force on this bar that accelerates it to the left, and then so this like would cause the bar to shoot outwards, depending on how strong your field is, how strong the current is, and how long it would be able to accelerate. And also things like friction would account too in the real world. But that is another scenario where you might be asked to apply, the Lorentz force, like similar to here. So like in this case, you're causing the bar to move at a constant velocity, and that induces a current. But if there's already a current through the bar, then the bar will start accelerating because of the force from this Lorentz force. All right, thank you very much.